All right, what's going on, everybody? Today we're doing another LeetCode video. This one is another medium tree problem. They basically want us to find the kth smallest element in a binary search tree. So we're given the root of a binary search tree, and we're given an integer k. They want us to return the kth smallest value, one indexed, of all the values of the nodes in the tree. So if they gave us let's look at this first example. So if they gave us k equals 1, obviously, just visually inspecting this tree, we can see that the first smallest value is going to be 1 here. And it's a binary search tree, so if you were to do an in-order traversal on this tree, the values would be in ascending order. So for this next example, they want us to return the third smallest value. So again, just by visually inspecting this tree, we can see that, the first smallest value is 1, second smallest value is 2, and then the third smallest value is 3. And that's in an in-order traversal. So we'd return the value of that third smallest node, which is coincidentally, 3. So in terms of constraints, k is going to be between 1 and 10 to the 4 inclusive. And then the values of the nodes are all going to be positive between 0 and 10 to the 4 inclusive. So not necessarily all positive because you can have 0, but they're going to be non-negative, right? So yeah, let's go ahead and get into whiteboarding for this problem. The way I'm going to do this is just with a recursive in-order traversal. So let's get into that code walkthrough or algorithm walkthrough. So let's say k, we'll follow that second input output example. So let's say k equals 3. So a couple of variables that we're going to need to pass by reference in our recursion. So really these are kind of like global variables. We just can't really have actual global variables in our code because it's bad practice, but we're going to have some function parameters that will pass down by reference to kind of emulate that behavior with more predictable code, more predictable and better code. So our first quote unquote global variable, and let me write these a little bit bigger, but we're going to have our result value at first. We can just make that -1. It doesn't really matter. We know we're going to find an answer by the way they described the problem. But anyways, we can just have that at -1 at first. This will be the actual value of that node that we're returning. We also need a variable to keep track basically of which node we're at from the smallest. So like once we would get to 1, I would be 1. Once we get to the second smallest, I would be 2. It's basically just counting nodes up from the smallest node. And at first this is going to be 0, obviously, until we get to this 1, and then we can start increasing it. So yeah, let's get into this algorithm walkthrough. So we're going to code our recursive function in a separate function, and we're going to seed it, and we'll call it first on this root node. So basically the first thing we're going to do is we're going to check, are we at a null node? That'll be like our edge case, or null pointer. And by the way, all of these, how are we going to do this? All of these nodes have left and right children, but sometimes those left and right children can be null, so or null pointer in C++. So I'm going to represent that with these dashes here. So anyways, we're going to check that first. The next thing we're going to do is search left. So we're obviously not at a null pointer here, so we can search left. So we're going to call recursive that function again, but on the left child. So we'll go this way. Is this node null? Nope. We're going to search left. Null, nope, search left, and we're going to keep doing that till we get to that null pointer. Okay, then we're going to pop back up because that's null, so we return. And the next thing we do whenever we pop up is we're going to increment this I. We're going to increment this I, and so that's going to turn into 1, right? So whenever we're popping up, we increment, so I is now 1. We can now search to the right, but before we do that, we're going to check, okay, is I equal to k? Once I is equal to k, we can set our result to whatever the value is at that node and then just start returning, right? But I is not equal to k yet, so we're going to search right. That'll be the next line of code. We're at a null pointer, so we need to pop back up. Okay, so now we're going to be at the code where we were in the function for this recursive call at this node. And the next line of code after searching left is going to be to increment I and then check if I is equal to k. So we're going to pop back up. We're going to increment I. So I is going to be equal to 2 now. And then we're going to check, okay, is I equal to k? It's not equal to k yet. So we can, the next line of code there will be to search to the right. And that's a null pointer. So we pop back up. And then we can, it's going to be the same exact thing that we did for the recursive call at this node, but for this node. So we return, we pop back up. We're going to increment I. So I is going to be 3. And we're basically going to check, okay, is I equal to k? Yes, it is. I is equal to k. So then we set the result to be whatever the value is at this node. So that result is going to become 3. And then we're going to have some code that basically puts the brakes on. So we're going to return once this result gets set to 3. This will be a variable by reference. And basically, so we return, there's not going to be any recursion this way. And I'm also going to have another if statement that basically once we backtrack this way, you know, at every one of these nodes, before we increment I, we're going to check, okay, is I greater than k? If it is, we don't have to do anything. We can just return, right? So that way we don't have to do these, you know, search this side of the tree at all, and it will just pop all the way back up without doing any unnecessary searching. So yeah, that's pretty much it for the algorithm. You know, obviously that return value is going to be 3 because of this node. And then the time complexity for this is going to be big O of n, because at the most, we're just going to have to visit every node once. You know, if they wanted like this, if k was 6 here, you know, we'd have to visit every single node. So big O of n time for the time complexity. And then the space complexity is just going to be big O of h, you know, or big O of log n, right? Where n is the total number of nodes in the tree, by the way. And then h is going to be the height of the tree. Which is also for a balanced binary tree is going to be log n on, you know, on average. So so big O of h space, and that is for the space that is required by the recursive call stack, right? Because we keep calling functions recursively, and basically the OS has to remember, you know, where we were at a, you know, a function when we start calling the same function recursively, right? There's got to be a way for the OS to like remember where you were, and that grows as big O of h. So with respect to the height of that tree. So let's go ahead and get into the code. So we're gonna need a couple variables, right? So our result variable, I'll just set to -1. And that'll be the value of the node, the kth smallest node that we return. We're also going to need count I, and we'll do that by reference too. So let's set that to 0. And then that's it for variables. And then we can seed this function. So we'll call, and it'll be a void function, so we don't have to set the return value to anything. So call depth first search on the root, right? We passed in the root at first. And then we also need that k, value k, to keep, you know, checking within this function if we've reached I equals k. Okay, we also need to pass an I and then result. And then after that, we can just return result. Okay, so let's actually write this recursive function now. So I'll put it as a private function member for our solution class. It'll be void, so it's not going to return anything. It's just going to return void. And I'll call it depth for search. So we need to pass in a tree node a pointer to a tree node. I'll just call that lowercase tn. And then we also need that k variable. So I'm going to pass it in as const reference because we're not modifying it, and we also don't want to make a bunch of copies of it. So const reference, because it's kind of like a target. And then we need our result integer. That'll be by reference, and we need to modify it so it won't be const. And same for our I counter, and I'll put that over here, so by reference as well. Okay, so those are the parameters, and then we need to check first if our tree node is null pointer. If it is, we can just return. The next thing we can do, since we're doing since we want to search left first, we want to call that function recursively on the left child of tree node. So we'll call it on that left child. K is the same, I is the same, and res is the same. And then before we search right, we actually want to, at this point, we would be popping back up from the searching as far as we can go left, right? Because we've already, the code is executed up to this point. If it got to the, bottom of the tree, it would return, and it would just keep it basically up to this point. We would have just searched left as far as we can go. So now, and we'd be popping back up. So we need to increment I. So I'm going to just do I++ to increment I. And actually, before we even do that, let's have a check just so we don't have to, kind of like at the end, once we've already found that smallest value, we don't want to keep searching needlessly. So let's say, if k is less than I, because the less than operator is actually a little bit faster than the greater than operator, so that's why I'm doing it that way. But we just want to return so we don't have to do any extra searching. So we'll just return, and then, okay, so now we're going to do I++, and we'll do that comparison to see if we found it. So if I is equal to k, then there's a couple things we want to do. We want to set that result value equal to whatever the value is at this tree node, and then we want to return. So now we can do the search to the right. So tree node, we'll call that search on the right child of tree node, passing k, I, res, all stays the same. And that's pretty much it for the code. So let's go ahead and submit this. So yeah, I hope this video helped you understand this problem better. If it did, leave a like and subscribe, and I'll see you guys in the next piece.